So we are finally going to get to the meat and potatoes of the lab, and that is the AA, which is atomic absorption. So we knew going into this that a penny is a metal, and a metal is copper and zinc, and that copper and zinc can easily be analyzed on an AA instrument without a problem. All right, so eventually we're going to get to the AA, and this is where we're going to do it. It's not the last part of the procedure, though, but it is another part that we can do that can contribute to this data. So the AA instrument, you know how this works. You probably have watched some of the lecture modules at this point. You've probably seen some of the previous labs that we've done with it at this point. You know how to set the machine up. You know how to choose the right bulbs and optimize the lamps. But the AA is going to be specific, and it's just going to look for copper, and that's it. The problem is that we're starting with a penny again, right? And because we're starting with a penny, we can't suck a penny through the nebulizer tube. That doesn't make any sense. We're going to have to dissolve this penny all over again, just like we did in the other lab portions. We're taking the solid sample, we're converting it over to a solution, and we're analyzing solutions. AA needs a solution. It needs a liquid to be pumped into the inside in the flame so it can free up the copper that it needs to measure. So keeping the penny as a whole solid is not going to do it for us. Well, in the previous part, what we realized is that we could take hydrochloric acid, but the penny would never dissolve fully. Copper would be left behind. That wouldn't be a very good acid to do, especially if we want AA to look for copper. If we don't dissolve the copper, it's not going to work. But in the second part, what we did is that we added nitric acid, HNO3. Well, that's great, because HNO3 dissolved the copper. But the problem with that is that we realized that not only did copper get dissolved, but zinc was dissolved as well. And that's why we had to go through all of those steps with those reagents to make sure that zinc would not precipitate out. It was a way that we could separate the copper precipitate from the zinc. That's why we used all of those reagents. Well, the AA doesn't care. What wonderful news. Because that means if I can take a penny and just dissolve it with nitric acid, as long as these solutions are on scale, meaning they're not too high, I should be able to go ahead and pump that solution through the AA and it would read it. Who cares if zinc's present or not? I don't really care if 100 different metals are present. If I have tuned the AA to copper and only copper, it will only look for copper. It won't look for anything else. This is what we need. This is going to make our life much easier, right? The problem here is that this is going to be an instrumentation signal, and we're going to have to be able to relate the signal to the concentration of the copper. And to do that, I need a calibration curve. Now, if you have taken the chemistry or the CTC 150 class, Standards and Solutions, you probably made a copper calibration curve and ran that on the AA already. And if you have that data, keep it. Use that data for this lab. If you don't have that data, or if you don't have those solutions left, then you probably need to make a set of standards all over again. So to make a calibration curve, we need to make some copper standards. The copper standards are going to come from a 1,000 part per million solution. And we're going to have to dilute that down to make a very good set to run on the AA instrument. Now, you probably are already aware that the AA has limits. It cannot go super high. So if we're going to pick the primary wavelength for the copper, that is going to determine what my concentration can and cannot be. All right, so here under the standard preparation, it says dilute 5 mils of a 1,000 ppm solution to 50. So it's going to tell me exactly how many I need to pipette out and what size flask I need to do and put it in. It's a 5 to 50. All right, so I'm going to go back to the notebook page, and I'm going to take 5 milliliters of the 1000, and I'm going to put it into a 50 ml volumetric flask. So this is going to require a dilution equation, right? MV equals MV. I'm starting with a 1000 ppm. I've taken 5 mils of it. I want to know what that new concentration is if I diluted everything to 50. So I need to do that calculation, and I need to figure out what the concentration of that diluted one's going to be. In the second step of the standard prep, it says then dilute that solution from above to make a 4, 2, and 1 part per million. Now, this lab only requires 3 standards. Your lab could require more than 3 standards, depending on the year and when you access this. Maybe it will, maybe it won't. This is also going to say must be done with the Buck AA. Well, that's because at the time that this was written, only the Buck AA was really provided in the laboratory. So it's going to be your choice. You can use the Varian or you can use the Buck. I don't really care which one you use. Either one's going to be okay. Either one will provide you data that you need. All right, so based on these directions, as of now, I just need 3 standards, a 4, a 2, and a 1. That also means you can't screw any of these up. All right, so from that bottle, a 4, a 2, and a 1. Does it tell me how much I need to make? Well, no, it doesn't. It just says dilute the solution to obtain a 4, a 2, and a 1. You can make whatever volume you want to make here. It doesn't say make 25 mils, make 50 mils, make 100 mils. We're going to leave that up to you, all right? You can make some of these decisions on your own. You just need to keep in mind that the machine will suck 10 mils of solution every minute. Do you need a full minute to analyze them? No. But what if there's something that gets screwed up with the machine? You're going to have to make them all over again. So kind of use that as a judgment to go by. You don't want to be wasteful, but at the same time, you want to make sure that you have enough to actually analyze more than once if something decides to happen. All right, so with these standards, you will make a calibration curve. And you make the calibration curve just like always. 0 is here. You have a 1, a 2, a 4, if that's the way this was going to work. You're going to plot the signals on the AA instrument, and you're going to draw a best fit line through that graph. So you're going to analyze these on the AA. You'll get absorbances for every one of these standards, and those absorbances are going to be plotted. This is your typical calibration curve generation. Nothing fancy, no tricks, nothing up my sleeve. Just run standards, plot them, get a line. It's as simple as that. Now, we're going to have to process the pennies. Again, we're going to have to get that solid penny down to a liquid. And we have to make sure that we are in the working range of the AA based on that lambda, that wavelength, primary wavelength. So number 1 says, cut 2 pennies in half using a large tin snip. Weigh the 4 halves and place them in a beaker or a flask and label them P1, P2, P3, and P4. Make sure that you record the exact weights down. In the hood, add 10 to 15 mils of 6-normal nitric acid to each and put it on a hot plate. Do not allow the solutions to go dry. You're going to have to add more nitric if you need it. So you don't want this stuff to go dry, right? You're putting it on heat. It's going to evaporate off. It just means keep an eye on it, people. Don't ignore it. Maybe you're doing something else in the meantime. You just want to make sure that this doesn't just boil and go to dryness. So after that, number 4 says cool the solutions and add 15 to 20 mils of DI water. So this, of course, is after you make sure that these are completely dissolved, right? You want your penny fragment to completely go away. When you do that, you add some water to it, increase the volume a little bit, And then it says, transfer each to a 100 ml volumetric flask, dilute to the mark with DI, and mix them. So this is our way of kind of tracking volume at this point. Up until this time, it's just roundabout numbers, right? Who cares what they are? Just add some stuff to it, add some water to it, make sure it's okay, and then transfer that over to a volumetric. And at this point, volumes are very important. Number 6, transfer each solution to a labeled bottle and store them. So P1, P2, P3, and P4. Number 7, dilute each of the above solutions 5 to 50. So we kind of have an idea of 2.5% copper in the penny. And if it's 2.5 grams per penny, we have an idea of what the copper should be, concentration-wise, right? And this is our way of knocking it down to a point that's suitable for the AA analysis. So we know what the anticipated amount is. If I didn't know that, there would be no way for me to know how I should be diluting these samples. It would just be a trial and error. I would dilute it, run it, see what I would get, and if it worked, great. If not, I would have to go back to the drawing board and make another dilution and try to figure out what the best way to do this would be. But I know the target. I know what should be present based on actual content or theoretical content, really. So that's why we're giving you the dilution steps. That's why this is required, a 5 to 50. But you know what? Number 7 is still too strong. So P1, P2, P3, P4, all with A's. That represents the very first dilution there. All right? But these are still too strong. We need to make them weaker, and that's number 8. Number 8 says dilute each of the above solutions from number 7, 2 to 50. And label those P1, P2, P3, P4 with B's and C's after them. Notice it says repeat to make another set. We want you to kind of analyze 2 of these and run 2 of them so you can get a really good average. That's why we're doing that. We're testing your dilution ability. Maybe you screwed up on one of the dilutions, and if so, we maybe possibly could leave it out of there. But we want to see 2 dilutions back to back that's giving us about the same type of number. Number 1 says, well, see the handout. Number 2, read all copper standards. Number 3, read only the B and C samples at the very end for step number 8, right? There should be 8 in total. P1, P2, P3, P4, representing the halves, and the B's and C's representing the duplicates. Number 5 says determine the part per billion or part per million of copper in the sample. All right, so here I would do the same kind of thing, y equals mx plus b. I would run a sample in step number 8 after I've done all the dilution, and I would get an absorbance read. That absorbance is then related to the regression line, and I would solve for x, and x would be the concentration in part per million. Okay, now here's where the tricky part comes in. This is where the math is at. So the calibration curve is going to give me the part per million of the diluted sample. And if I go back to the directions, look, this was diluted a factor of 2 to 50. All right, well, I need a back dilution here. CV or MV equals CV or MV. All right. The concentration that I get from the AA, that's the final concentration. That's what I ran, right? So let's say that my number gives me a 2 part per million. Well, I've made a 2 part per million, and that was from a 50 mils in total, right? Because that was my final volume. It was 50 mils, and that's what I ran in that 50 mil flask. Well, that came from a 2 mil solution, a stronger one. So I don't know what that concentration was, and it came from 2 mils in total. I want to know what that concentration was because it made the one that I ran. So I'll take 2 times 50, which is 100, and 2 times x, which is 2x, divide by 2, and x is equal to 50. All right, well, this is 50 part per million, and that would be great. The problem, though, is that that was also diluted, right? Because it said dilute each of the above 5 mil to 50. So this solution is the one that ran 50 part per million, and I need to take one more step to get to the original. And that original, I had 5 mils of it, diluted it to 50. So I need to do this one more time. So over here to the side, I'm going to kind of represent that a little bit. So based on the number that I just made up here, this is from the Cal curve. Remember, whatever Cal curve number you get goes there. I just made it up. So this is a 50 part per million, and it looks like that came, hold on, it looks like that came from a 50 volume. And I want to know what's the concentration of the original, and it looked like I had to take 5 mils of that. So I'm going to put 5 in for here. So I took 5 mils of the original, diluted it to 50. That gave me a 50 ppm. And then I took the 50 ppm over here to the left. I took 2 mils of that. I diluted it to 50, and I got a new concentration. So I've got to work this one more time. All right, so 50 times 50, and then that gives me 5x. I'm going to divide by 5, and x is going to be here around 500 part per million. And this represents my original. So 2 back dilutions are going to be required. And that's how we'll do them. Just like a normal dilution, you just got to keep in mind, it came from another flask, right? So this is the flask that I ran on the AA, but this was made from another flask. And the way that we did that is that we took 2 milliliters of this stuff, we diluted this one to 50. So that's why we did our first back dilution. This 50 ppm represents this concentration. The problem is that that came from another one. So that is why we have to do this again. So this is, according to my math, the 50 part per million. I want to know what is the concentration of the original. We took 5 mils of that one and diluted it to 50 milliliters. So according to my math, this is going to be a 500 ppm. So maybe that drawing will help you kind of visualize what's happening here, but we have to backtrack twice in order to get to the starting point. All right, well, when I do that, this part per million is going to be based of milligrams per liter. And there's a couple of ways that we can continue with the math here. And I'm going to kind of explain maybe both of them and show you which way that I would prefer your spreadsheet to be set up as. So let's say that we have a 500 part per million solution calculated as our original. That means there's 500 milligrams for every liter of stuff. All right, well, the problem here is that I did not make a liter. What happened is that I took that penny and I dissolved it, and I brought that penny to a total volume of 100 milliliters, right? And that is what we used to start making the dilutions with. We took 5 mils of that, went to a 50, then took 2 mils of that, and went to another 50. But in the beginning, I did 100 mil in volume. So that 500 part per million is milligrams per liter, but I didn't make a liter of solution. I made 0.1 liter. So that means I've got to take another step. This is 500 milligrams for every 1 liter. I want to know how many milligrams I would have if I only did 100 milliliters, which is 0.1 liter, in the lab. So I would take 500 and I would multiply by 0.1, and that would give me 50 milligrams, right? You cross multiply and divide. 500 times 0.1 equals x times 1. So multiply those two, divide by 1, and you'll get 50 as an answer. 50 milligrams. So that weight, I would divide by the weight of the penny. The problem, though, is that you probably need to change this to a gram, because you're probably going to have gram for your penny weight, and you need those units to be the same. Then you're going to multiply by 100 like you always have, and that will give you the percent of copper based on your half penny weight. Remember, you took the sample, cut it in half, so you're only looking at that particular halve's weight to calculate this, just like before in part 2. All right, so that's one way. The other way that we could do this would require you to kind of think about the 2.5%, and this will give you the percent of copper. And then you can compare that to the real percent of copper from the mint. All right, so that's how we would do percent error basically there. The other way that we could do this is that we would assume that our starting gram for our penny would be prim and proper of 2.5% copper. So we could calculate the gram of copper that's present, and then I could change this to milligram of copper that's present, and then I could divide by 0.1 because that's the volumetric flask size that I used, and that will give me my copper part per million. And this would be if it was 2.5%. This is what my copper part per million solution would have been. And then I could compare that to the original part per million from my calculation. It's just another way to look at it from the top down, or instead of the bottom up, right? I know what the actual should be. I can calculate what the solution should be and compare that to the strength, or I can work backward. And I can take that volume, part per million, and that 100 milliliter, and go backward to get actual milligrams of copper that was present. Now, which way do I want you to do it? That's always the question. Well, here's the AA for the procedure. And it looks like here's my penny number 1, 1.2113. I diluted that penny to 100 mils. So this would be an expected target concentration, right? Here's the milligram per milliliter, because the lab procedure wanted me to do it this particular year. Yours might ask for it, or it might not. It says diluted 5 to 50, so that would be the new concentration there. And then I did a 2 to 50, so that would be the new concentration there. And then I did another 2 to 50, and that would be the concentration there. So I'm basically making you work. If the entire weight was copper, if the entire thing was copper, it looks like this would end up being a 1.93808 concentration. All right, and I did that to this half for penny number 2, and I did it for penny number 3, and I did it to penny number 4. All right, well, here are the standards. There's the standard concentrations, and there's the absorbance values. And these were the absorbances that I got from the pennies. So we plugged 0.1492 into the line. We solved for X. And when I did that, that gave me a 1.46. So this 1.46 was milligrams per liter of my diluted sample in the very end. So I had a 2 to 50 dilution, so I corrected for that. And then I had another 5 to 50 dilution, I corrected for that. And then I calculated the actual number of milligrams that was present. Because I didn't make a liter, I made 0.1 liter instead. So I ended up with 36 milligrams, give or take, of copper in the sample. I took that 36 milligrams, converted it to gram, then divided it by the starting penny weight, which was 1.2113 gram, and that allowed me to calculate my percent of copper. 3.0 is what this person got based on their data. Well, they did it 8 times, So we did an average over here, a standard deviation, the accepted value, 2.5, and there's my percent error. So based on the data, it looks like the atomic absorption instrument was worse than the chemical gravimetry. But you know, this all is based on settings of the machine and how good were your standards. If your standard prep was awful, if you didn't set the machine up the proper way, then your results are bogus. It doesn't really mean anything at all. So all of that is dependent on the user. Now, the reason that I did this up here at the very top, and the reason I introduced it, is because I wanted to show you the thought process of why we picked the standards that we did. So we're going to assume that maybe everything here is going to be copper. And notice that I've weakened it down to get a target range. It looks like these would run on par of about 1.9 part per million, somewhere in there. And look at what all my numbers were reading, right? 1.4, 1.4, 1.5, 1.5, 1.3, 1.3, 1.2, 1.2. So this is why we've focused our standard curve around that number of 4, 2, and 1, one above and one below. Again, your lab directions might make you make more than 3, and if so, then do it, but the process is still the same. But this is why we picked the standards that we picked. And some people have questions on that sometimes. They don't really understand, well, where should I start with my calibration curve? Well, we kind of have an idea of what's present. We have an idea of what the concentration should be in the very end after all of these dilution steps, and we're going to build our calibration curve around that, and that's why we do it. So on your spreadsheet, if it doesn't ask you to do this, then don't do it. The only thing that we need from you is a calibration curve with some standards and a regression line, and your absorbances plugged into that regression line, and you need to backtrack with the concentrations, one after another, to get to this percentage of copper. That is what this lab is after. So unless it specifically states for you to do this, don't do it up here at the very top. This was just a way for me to kind of show you why we picked the calibration standards that we picked. All right? So this piece that you're seeing on the screen right now, that's probably the only piece that's going to be required from you when you do this spreadsheet. Okay, so good luck with the AA. Remember, the data is only as good as the user for the instrumentation, and you want to be very careful when you make your standards. You want to make sure that lamp is really optically aligned and that it is maximized to its full potential before you start running all of these samples on the machine. Don't trust that someone else has done it before you. Because if you do, and their numbers are wrong, it's going to make your numbers wrong as well because you didn't double check it. So always double check the instrumentation settings before you run it. Again, Varian or the older AA, doesn't really matter which one you use. Both will give you some numbers that you can use. Not a big deal at all. So just because one looks a little older than the other doesn't mean that it's better or not better. All right, guys, so good luck on the AA. We're almost finished. We've got another part that we want to talk about, and that's using another piece of equipment that we talked about this semester.